Good morning. All right, we're going to pick up where we left off last week. This is section 1.2 still. We got a few more examples to finish up here, and then we'll move into 1.3. If you didn't already notice, I moved the homework back to Friday for now. It might even get pushed back even further than that, but I wanted to make sure that I at least gave us today and tomorrow to finish up 1.3 and 1.4. And if we don't do that by tomorrow, then I'll push it back into next week. But continue to work on the 1.1 to 1.4 homework. Definitely send me questions using the Ask My Teacher button as you have them. And definitely feel free to drop into my student hours if there's anything that you need me to work through with you. Okay. The only other thing I'll mention is if you haven't already completed the Respondus Lockdown Browser Assessment, please make sure that you get that done. Our first test is probably coming up towards the end of this month. And so I just want to make sure that you've at least done the practice assessment before we get to the first test, so that you can make sure if you have any issues, we can get those resolved. If you still don't have a device and you've requested one, I know they received a lot of requests at the beginning of the semester, so they're a little behind on that. Just try to be patient, and I can definitely give you an extension on that. If we don't have any word by next week, then we might have to look for other solutions, once we start getting closer to that first test. But for right now, just try to be patient, and whenever you do get a device, I can let you complete that assessment. But if you already have a device and you're still having issues, definitely let me know so we can get those things worked out. Okay? Any questions, comments, concerns before we get started today? All right. So, like I said, we're going to pick up with 1.2. This is radicals now. So, remember last week we started working with exponents and we looked at all of our laws for exponents and what we can do with those. Well, now we're going to go the other direction, right? So, we're actually taking square roots, cube roots, those types of things of different values. And so, in this case, it tells us the square root of A equals B just means that B squared is equal to A. And in this case, the B value is going to be greater than or equal to 0. And the reason for that is anytime we take an even root of a number, right, a square root, a fourth root, a sixth root, or so on, we're always going to get a positive value or 0, right? It could be equal to 0. We're never going to get any negative values out of any of those roots, okay? Now, if n is some positive integer, we can say that the principal nth root of A is defined as follows, okay? So the nth root, so notice here we've got this little number right here. We're going to call that number the index of our root. Okay, so this is the nth root of A equals B, means that B to the n power is equal to A now. If that n value is even, like the square root that we just looked at, then the A value has to be greater than or equal to 0, and the B value also has to be greater than or equal to 0. Okay, so we have to have a positive value or 0 on the inside, and then the value that we get out of that root is also going to be a positive or 0 value. If that n value happens to be odd, we can actually take odd roots of negative values. Okay, so like a cubed root or a fifth root, if we have negative values inside, that's perfectly fine. And we can actually get negative values as our result in those cases also. Okay. Okay, now some properties of these roots. Okay, so if we're taking the nth root of A times B, we can actually split up that root into multiple radicals. Okay, so we can take the nth root of A and take the nth root of B and then just multiply those two things together. The reason this is useful is sometimes you'll actually be able to take the nth root of one product, part of your product on the inside, but not the nth root of the other. And so then we can say, okay, yeah, let's break it apart. Let's take the nth root of what we can, and then let's just keep whatever else is left over on the inside. Okay, and so you are allowed to split up products on the inside into multiple roots. You do the same thing with division. Okay, if we have division on the inside of a radical, we can actually split that up into the nth root of A divided by the nth root of B. Okay, so multiplication and division, we're allowed to split up like that. If we have a root within a root, okay, so notice here we've got two different indexes, right, or indices. The nth root of the nth root of A, we can actually combine those into a single radical, and we're just going to multiply the two indices together, right? So the m and the n get multiplied together, and we write that as a single root at that point. And then finally, these last two are very similar. One is if n is odd, the other is if n is even. So we have the nth root of a to the n power is just going to be equal to the a value, whatever that happens to be, as long as our n value happens to be odd, right? So we're taking an odd root of a to the nth power, we're always going to get a. If we're taking the nth root of a to the n and n happens to be an even root, then we just have to remember to put absolute value bars around the a value because we know in this case that we need to get a positive value anytime the nth root is even. And again, all of these are in the slides, right? So feel free to look in the course content section if you ever need to look back and see these properties, and I'll come back and address them as we need them in actual examples also. All right, so let's take a look here. Example 9, we want to take the cubed root of x to the 4th power now. All right, so the first thing I'm going to do when I see a problem like this is I'm going to try to create groups of 3 x's, right? Since I'm taking a cubed root, I want to get as many x cubes inside that radical as I can. So is there a way that we could rewrite this cubed root using groups of 3 x's instead, right? So rewriting x to the 4th as x cubes with something left over. What would that look like? Good, right? So we could rewrite x to the 4th as x to the 3rd power times x to the 1st power. Because remember, our properties of exponents say that we would add those exponents together. 3 plus 1 would give us 4. So that's now equivalent to what we started with. Now, at that point, because we have a product inside, we can use those properties of radicals that we just looked at. So we can actually split this into 2 separate radicals. And I'm going to rewrite this as the cubed root of x to the 3rd times the cubed root of x. And then at that point, we can simplify whatever we can. Right? So what is the cubed root of x to the 3rd going to give us? Good. It's just going to be an x, right? So remember that one said, as long as that's an odd index, those 3's just cancel out, and we're just going to get the x. Now, the cubed root of x, we cannot do anything with that, right? So I'm just going to bring that down and keep the cubed root of x here. And so this right here would be our simplified answer for the cubed root of x to the 4th. So again, always look at your index, create groups that are that large. So in this case, it was a 3, so I created x to the 3rds. Right? And then whatever's left over, that's going to have to stay on the inside. Whatever we can bring out, we're going to bring out. Any questions on that one now? Okay, so let's look at the next one now. Same thing. I want to try to create groups of 4s this time because I have a 4th root. And so when we look at these things, I'm going to keep my number this time. That's just going to be the 4th root of 81. If I want to create groups of 4 x's now, how could I rewrite x to the 8th power? Good. That's going to be x to the 4th power times x to the 4th power. Because again, properties of exponents, we would add those exponents together. 4 plus 4 would give us the 8 that we started with. And then our y to the 4th is already a group of 4, so I'm just going to leave that as y to the 4th. All right, now, at that point, I'm going to use that property that says we can split up multiplication into multiple radicals. So the first thing I'm going to do is I'm going to take the 4th root of our number here, so 4th root of 81, times then I'm going to have a fourth root of x to the fourth times the fourth root of x to the fourth again times the fourth root of y to the fourth. Now I'm going to go through and actually take the fourth root of each of these things, right? So what is the fourth root of 81? Good. It's going to give us 3. So this value right here is 3 because 3 times 3 times 3 times 3 is equal to 81, right? So the fourth root of 81 should give us a 3. What's the fourth root of x to the fourth going to give us? Okay, it is x. Now, in this case, remember, because it's an even root, what else do we have to put on it? Has to be the absolute value. Good. So this is going to be 3 times the absolute value of x. And then that next fourth root of x to the fourth is going to give us the same thing. So we're going to have another times absolute value of x. And then what are we going to get for the fourth root of y to the fourth? Absolute value of y. Perfect. Now, once we've taken everything out of the radicals that we can, the only thing left is to simplify if we have any like terms. What's the absolute value of x times the absolute value of x going to give us? It's going to give us an x squared. Good. And notice here, we don't actually need the absolute value anymore because x squared automatically is going to give us a positive value. So we can actually just write this as 3x squared and then bring down the absolute value of y. So this right here would be our simplified version of what we started with. Any questions on any of the steps for that one now? Yeah, so what I would do in this case, right, is go ahead and keep the absolute value bars until they're no longer necessary. So it's once I actually multiply those two absolute value of x's, I know x squared is already positive, I can drop the absolute value bars at that point. Okay. All right, so Christina, there is technically a shortcut to this. So that's what I was going to show you next. So for this one, right, I wouldn't necessarily need to see all of these steps. One thing that makes this one kind of easy is my exponents are actually divisible by the index that's on the outside. So in this case, if I take the fourth root of 81, we already said that's going to give us a 3, right? So I'm going to bring down my 3. Then I'm going to take the x to the 8th, and because I'm taking the fourth root of it, I'm just going to divide the 8 by the 4. Okay, so I'm taking the exponent that I have, I'm dividing it by the index that's on the outside. Now notice this is only going to work if those two numbers are actually divisible by each other. This would not have worked on the previous problem because I can't divide 4 by 3 to begin with. Okay? And then we have in this case a y to the 4 divided by 4. Now, technically in this one, because it's still an even root, I do need the absolute value bars on my x and my y as I'm doing this. Okay? Now, what is 8 divided by 4 going to give us? 2, right? So this is going to give us 3 absolute value of x squared, but we already said that's automatically going to be positive, so that's just 3x squared. And then what's 4 divided by 4 going to give us? It's just a 1, right? And so we know that exponent is understood, and so we don't have to write the 1. We can just write this as absolute value of y. Again, that's the same thing that we just got there. So if your exponents are divisible by your index, then you can actually just divide them and get the same answer that we got by breaking everything down that way. But again, in general, if it it's not divisible, then you're going to have to break it down anyway, right? And so just always think I want groups of whatever my index is. And so the first one was 3, so I did x cubes. In this case, we had a 4th root, so we wanted to do it in groups of 4. Bring everything out that you can. And then anything that doesn't come out, right, just make sure you leave it inside the radical. In this case, we had nothing left over inside the radical, but the first one we did. Yeah, so that is kind of the shortcut, right? And again, it works as long as you can divide the exponents. But if you can't, then you're still going to have to go back. But again, on the first one, once I got to this first step, then I could say, oh yeah, 3 divided by 3 is just 1. So that's x to the first power. And then I'm left with this cube root of x. Right? So you don't necessarily have to write that intermediate step if you don't want to. If you start to remember those shortcuts, feel free to use them. Any other questions on either one of those now? All right. So now we got some actual numbers in here. All right, so we got the square root of 32 plus the square root of 200. We want to see if we can simplify that. Now, for addition and subtraction, we can only combine radicals if they have exactly the same root with the same number inside. So here, the square root of 32 and the square root of 200, we can't add those together as is because the 32 and the 200 would need to match. So what I want to do first is see if we can simplify these square roots. And then if we happen to get the same square root, the same number inside the square root, then we can actually combine those like terms. Are there any values that go into 32 that I can actually take the square root of? That's my question here. Okay, so is there a number that divides evenly into 32 that we can take the square root of? 16, right? So in this case, I'm going to break down the square root of 32 into 16 times 2. 16 times 2 would be 32, and 16 is what we call a perfect square because I can take the square root of 16. Now I want to do the same thing with 200. Is there a number that goes into 200 that I can take the square root of? 100, right? So 100 is also what we call a perfect square. We're going to break this into 100 times 2 now. Now, there are other perfect squares that go into each of those, right? I could have used 4 for the first one. I could have used 25 for the second one. Always try to find the largest perfect square, though. That's going to help us to simplify it the fastest. Okay, but if you don't see the biggest one, it's fine. You'll just have to go through more steps to get to the final answer. Now, once I have that, remember, we're allowed to split up multiplication into multiple square roots here. So I'm going to rewrite this as the square root of 16 times the square root of 2 plus the square root of 100 times the square root of 2. And again, if you don't want to write out that step, that's perfectly fine. If you can just see what it's going to be, you don't need to write that out. Now, what is the square root of 16, though? Four. Good, right? So square root of 16 is going to give us 4. I'm going to bring down my square root of 2. What's the square root of 100? Good. And then we have our square root of 2. At that point, we have a square root of 2 in both of our terms, right? So now we have like terms, and I can actually combine these. If I add 4 square roots of 2 to 10 square roots of 2, what's my answer going to be then? Perfect, right? So we're going to get 14 times the square root of 2, and this is going to be my answer now. Right, so the way I kind of think about this, square roots of 2 now become like a variable, right? So that's what makes these like terms. So it's like saying we have 4x's plus 10x's, that would be 14x's. In this case, they're square roots of 2, so there's 14 square roots of 2 now. Any questions on that one? That's right. So we don't add what's inside the square roots, right? We're going to keep that as the common factor, basically, right? That square root of 2 is what they have in common. We're just going to bring that down. So only add the numbers on the outside, keep whatever's inside the radical exactly the same. That's right. Yeah, another way to think about that is because they have the square root of 2 in common, I could rewrite this as square root of 2 times 4 plus 10 by bringing out that common factor of square root of 2. Then I'm adding together the 4 and the 10, so I end up with square root of 2 times 14, which is exactly what I have there, right? 14 square root of 2, but that's why I don't need to add together the 2's that are inside the radical, right? I'm bringing that out as a common factor now. Okay. Any other questions on that one? All right. Now, one thing that you're probably going to want to work on, right, if you don't know your perfect squares already, right, that's what you're going to need to be able to do to simplify these. Let's just kind of make a list here. I'm going to start with 2 squared, right, because 1 squared is just 1. It's never really going to help us too much. So what would 2 squared be equal to? 4, right? So 2 times 2 is 4. So that gives us one of our perfect squares. What about 3 squared? What's 3 squared? That's going to be 9, right? So 9 is also what we call a perfect square. What about 4 squared? 16. 5 squared is 25. 6 squared, 36. 7 squared, 49. Good. 8 squared, 64. 9 squared is 81. 10 squared is the one we just did. It's 100. 11 squared, 21. And 12 squared, 144. If you know those by memory, right, that's probably as far as you need to go. Obviously, you can go all the way up. Knowing up to 20 is nice, right? But if you know up to 12, that's probably going to be sufficient. And then you can always use your calculator to figure out the others if you need to. Okay, but I would definitely commit those to memory. Just be able to kind of know those off the top of your head, because those are the factors you're going to be looking for when you're simplifying these radicals now. Okay. So look at the next one. Okay, so they tell us here that b is greater than 0. That's just to make sure that we have a positive value inside our square root here. So we have 25b inside the first square root, and we have b cubed inside the next one. So what could we do in this case to simplify this so that we could actually maybe combine them? Okay, so what are we going to split that b into? B squared times b. Good. So actually, I'm going to go ahead and break up this first one here. I'm going to rewrite this as square root of 25 times square root of b. And then the other one I'm going to write as the square root of b squared times the square root of b. Because again, you would add those exponents together. 2 plus 1 would give us the 3. Now we can start to simplify these, right? So what is the square root of 25 going to give us? Should be a 5. So we get 5 times the square root of b minus, what's the square root of b squared? Okay, good. Now, in this case, technically, it would be absolute value, right? But they already tell us that b is greater than 0, so that's why we don't have to have the absolute value this time. So we're just going to have a b times the square root of b. And now we actually have like terms, right? Because we have a square root of b in common for both. So we can actually just rewrite this now as the square root of b times and then we have 5 minus b left over. So this would be our simplified answer now once we actually take out that common factor of square root of b. Now, honestly, if you leave it at the step before, I'm not going to take off any points, right? It's technically okay that way. You've brought everything out of your square roots that you possibly can, but just another way to write that now, because there's that common factor, we can actually bring that out. Any questions on that one now? All right, let's look at the third one. Okay, so we got square root of 49x squared plus 49. What do you think we might want to do with this one first? All right, so we don't want to square 49, right? So the question is, can we reduce the 49 to 7, right? Because I think you can look over here at our list. 49 is a perfect square, right? So you're like, oh, let's take the square root of 49. Now, the issue here is that we don't have any properties that deal with addition inside of a square root, right? Everything has to be multiplication or division. We're not allowed to split up addition. So I can't just go in there and start taking the square root of the 49, the square root of the x squared, and the square root of the other 49 because there's that addition between them. I need to create some kind of multiplication or division in here so that I can actually split this up, and then I'm able to take the square root. So is there anything we could do inside that square root now that would give us some type of multiplication or division? Okay, so we don't want to rewrite the x squared as x plus x, right? Or because I mean that would actually be x times x even if you did that. So we can't do that. So think about your terms that you have inside here, right? So we have the 49x squared and we have the 49. Is there anything they have in common? Okay, they have a 49 in common, right? 7 squared is the same thing as 49. Okay, but they have that 49 in common. So what I want to actually do on this one is let's factor out that common factor. So I'm going to keep my square root, but I'm going to factor out this common factor of 49 now. What would that leave us with if we factor out the 49? Good, right? So the first term would still have an x squared, and then we always have to have that 1 to hold the place for the other 49, right? So hard to distribute that back out. 49 times x squared is 49x squared. 49 times a positive 1 gives us the plus 49. Now I've created multiplication inside there. I have 49 times x squared plus 1. So I'm allowed to split that into 2 separate square roots. We're going to have the square root of 49 times the square root of x squared plus 1. What's the square root of 49? 7. Good. All right, so that's going to give us a 7. Now, we have the square root of x squared plus 1. Can we do anything with that? And no is an acceptable answer if you think it's no. Okay, so it looks like, oh yeah, I've got an x squared, I've got a 1. Both of those are perfect squares. Let's take some square roots out. The problem again is we have addition in between them. We're not allowed to split up addition. So there's really nothing else we can do in this case, right? X squared plus 1 does not factor. We're not allowed to split up the addition and take the square root of each of those values. So I have to just keep this as the square root of x squared plus 1. And this is as much as I can simplify that one, okay? So be very careful, right? Because it's really easy to kind of get carried away and say, oh, yeah, I've got two perfect squares in there. Let me just take the square root of each one. If there's addition or subtraction, you're not allowed to split that up, okay? Any questions on that one now? Okay. And just to kind of give you an example of why we're not allowed to split up the addition, you can do it with actual numbers. It makes it a little more clear why we cannot do that. Okay, so let's say I had something like square root of 16 plus 9. According to order of operations, what would I need to do first? Add them, right? So the square root counts as a grouping symbol. It's like parentheses now. So I would actually add together the 16 and the 9. So that's going to give me the square root of 25. Well, what's the square root of 25? 5, right? So square root of 16 plus 9 should just give us 5. If I were to try to split this up, though, right, I would have the square root of 16 plus the square root of 9. What's the square root of 16? 4. What's the square root of 9? And what's 4 plus 3? Not 5, right? Okay, so this over here is incorrect math. Don't try to split things up like that, okay? So that's why, again, down here at the bottom, that x squared plus 1, we can't split it up. Because taking the square root of x and taking the square root of 1 and adding them together is a lot different than adding those things together first and then taking the square root, okay? So this is the correct math. Separating them like that is incorrect math. Don't do that. Any questions at all on those three problems now? All right. Now, rational exponents. Okay, so just like we looked at exponents with integer values before, we can also have rational numbers. Remember, that means fractional values in our exponents as well. Okay, so we're going to have m and n being integers, right? So we're going to have an integer over an integer that creates a fraction. N cannot be 0 because we can't divide by 0, so you can't have 0 in the denominator. But a to the m over n power now can be rewritten as a radical where m becomes the exponent on the outside and n becomes the index of our radical. And notice here, it could be written this way or this way. It doesn't matter whether you put the m power on the outside or the inside. Those two things are equivalent to each other. Okay, but just know the n is the index and the m becomes the exponent. And then like before, if we have an even n value, then we require that a has to be positive or 0 because we can't take an even root of a negative value now. All right, so let's actually do an example here. So we got 4 to the 1/2 power. So we want to rewrite that fractional exponent using radicals now, and then we'll simplify where we can. So what is this one going to look like if we rewrite 4 to the 1/2 power using radicals? Good. It's square root of 4, right? So the 2 becomes the index. So that's the index. And then we're going to have 4 to the first power inside there. Just remember the 1 becomes the exponent, the 2 becomes the index. And in this case, technically, right, we don't need the 2 as the index. Square roots have that understood too. And then 4 to the first power is just 4. So you can actually rewrite that as just square root of 4. And what is the square root of 4? 2, right? So we get the square root of 4 is just 2. Any questions on rewriting or simplifying that one now? All right, let's look at the second one. How could we rewrite 8 to the 2/3 power? Good. 3 goes in the index, 2 goes in the exponent, so we're going to have a cubed root of 8 squared. Now we want to simplify if possible, right? So what would you do first here? Okay, good. We can square the 8 and give us the cube root of 64. And what is the cube root of 64? Good, right? 4 times 4 times 4 is 64. The cube root of 64 is 4. Now, remember, it said that we could actually rewrite this as the cube root of 8 and then square all of that, right? So another way to write this one would be the cube root of 8 all squared, right? It doesn't matter whether the square goes on the inside or it goes on the outside as long as it's in the exponent. In this case, though, what would you do first? You would take the cube root of 8. What is the cube root of 8? 2, right? So now we end up with 2 squared. And what is 2 squared? 4. Notice, same answer we got the other way, right? So those two things are always going to be equivalent. It doesn't matter which way you do it. Okay, so if you want to take the cube root of 8 first and then square that value, or if you want to square the 8 and then take the cube root, you should get the same answer. The only reason I point this out is sometimes, right, it's easier to go ahead and do the root first to keep your numbers smaller, because you might not recognize the cube root of 64, but you say, oh yeah, the cube root of 8 is 2, and I know how to square that, and so it might be easier to work with it one way or the other, okay? All right, now we got our last one here, 125 to the negative 1/3. What's the first thing we should do this time? Get rid of the negative. Thank you. Good. So if we get rid of the negative exponent, how are we going to do that? Think back to our rules that we looked at last week for negative exponents. How do we get rid of a negative exponent? Good. We're going to move it to the denominator, right? So we're going to put 1 over 125 to the positive 1/3 power now. So always get rid of that negative first. Now we've got 125 to the 1/3 in the denominator. How can we rewrite that? That becomes the cube root of 125. So we have 1 over cube root of 125. And technically, that's to the first power, right? So if you want to put that 1 there just to remember. But what is the cube root of 125? Just 5. Good. So we have our 1 in the numerator. We have our 5 in the denominator. So this all just simplifies to 1/5. Any questions on that one now? Now, just so you know, right, if you were to put these in the calculator just like they're listed here, it should still give you those same values, right? Just make sure that the fractions themselves are in the exponent. On some graphing calculators, right, like the first one here, you're going to use your caret key for the exponent. You might have to put parentheses around your fraction. It kind of depends on how your calculator operates. Some of them automatically move you into the exponent and you can actually put in a fraction. But if it doesn't do that, okay, then just make sure you group together the 1 divided by 2 there for the 1/2. But when you do that, it should give you 2. Same thing with 8 to the thirds. If you put that in the calculator, it should come out that way. Okay. So you're allowed to use the calculator on everything that you do in my class, right? Homework, test, final exam. I will ask though that you still show me your steps, right? So the calculator is more there to kind of check yourself, but I still do want to see the steps for the process to make sure you understand how to actually simplify these things. Okay. Any other questions there? All right. So now we've got some variables here. So we want to work on combining and simplifying. So if we've got a to the 1/3 times a to the 7/3, what would be the first step to that problem? Good, right? So we're multiplying bases. We would add the exponents. And so when we add those together, we're going to have a to what power? So it's 1/3 plus 7/3. 8/3, right? Because we would add the numerators, keep the common denominator. That's going to give us 8/3. Now, at that point, we can rewrite this using radicals, right? So what would this look like in radical form? Good. So we have a cubed root now because the 3 becomes our index. And then we're going to have an a to the 8th power now. All right. Now we just want to simplify if possible, right? So if we're taking the cube root of a to the 8th, think back to that first example we did today, how could we break this down to simplify it? Okay. So we have an a cubed and a to the 5th. Can we take out any more groups of 3 than that? Yeah, we could do an a cubed, and then an a squared, right? So I'm going to break this into a cubed times a cubed times a squared. Always look for as many groups of 3 in this case as possible, right? So that we can bring out as much as we can and then only leave whatever's left over. Now I'm going to take the cube root of each of those, right? Because I'm allowed to split up each of those products. So what's the cube root of a cubed going to give us? A. And then the cube root of the next a cubed would be another a. And then left inside then is the cube root of a squared, right? Because we can't take the cube root of that now. Then our last step is just to multiply whatever we brought out. So what's a times a? Good. So we have a squared times the cube root of a squared. Any questions on that one now? All right, so look at the next one. So what's going to be our first step on the next one? Good. Let's add the numerators, right? So when we add those exponents, what do we get? 9/5. Okay, so we have a to the 9/5 over a to the 3/5. All right, what's our next step going to be? Good. Now we can subtract, right? Because remember with division, we're going to subtract exponents. And so what is that going to give us for our exponent then? Good. A to the 6/5. Now, because we have that fractional exponent, we want to rewrite that as a radical. So what's that radical going to look like? Good. 5 is the index. Fifth root. 6 becomes the exponent. A to the 6th. Okay, now we want to see if we can break that down and simplify it. Okay, so can we break down a to the 6th so we can take a fifth root out? Good. So we're going to have a to the 5th. Remember, this is multiplication, right? So times a. Now we can take the fifth root of each of those. So what are we allowed to bring out this time? What's the fifth root of a to the 5th? That's going to give us an a, right? So we bring out an a. Can't take the fifth root of a, so that's going to stay the fifth root of a. And that would be our final answer there. This kind of combines everything that we did last week and today, right? Remember your properties of exponents. Multiplication becomes addition of exponents. Division is subtraction of exponents. And then once we get those fractional exponents, then we can actually change those to radicals, and then we can simplify the radicals where possible. All right, what about the next one? What's our first step going to be? Okay, good. So we can distribute that exponent to each of the terms inside here. So we're going to get 2 to the 3/2. Then we're going to have a to the what power? Good. Multiply those together. So that's 9/2. And then we're going to have b to the what? Good. And what is 12/2? Just 6, right? Okay, so 4 times 3/2 is 12/2, which just simplifies to b to the 6th. All right, now we can rewrite what we need to as radicals, right? The b to the 6th is just going to stay like that. The other two, though, will become radicals. So this is now going to be the square root of 2 to the 3rd power times the square root of a to the 9th power times b to the 6th. All right, now we want to rewrite these so we can actually take square roots out. So what's 2 to the 3rd power? It's going to be 8, right? Can we break down 8 so that we have a perfect square that we can take the square root of? Yeah, 4 times, not 4, but 4 times what? 4 times 2. Good. Right. So another way to think about this is like 2 squared times 2, right? If you want to do it that way. And I know we're out of time. I'm going to try to finish this one up and then we'll stop. And then over here, a to the ninth, what I'm going to do instead of breaking it down into a whole bunch of a squares, I know 8 is divisible by 2, so I'm just going to call this a to the 8th times a, and then I can use that little shortcut where I divide the 8 by the 2. Right, so then if we simplify all this now, square root of 2 squared is going to give us what? 2. Good. Bring down the 2. Then we're going to have the square root of a to the 8th would give us what? A to the 4th. Good, because remember that's that shortcut. We're going to divide the 8 by the 2. It's going to give us a to the 4th times the square root of a, and then we'll just have our b to the 6th. And there's nothing else that we can do there. If you wanted to combine the square root of 2 and the square root of a, you could. So technically, you could write this as 2a to the 4th, b to the 6th, and then put the 2 and the a back inside the square root together. All right, so that answer right there would be fine. Okay. All right, so again, I'm sorry we went over a little bit today. That's where we'll stop. Again, continue to work on homework. It's probably going to get pushed back into next week, so you'll at least have the weekend to get it done. But we'll get as far as we can tomorrow. Let me know as you have questions. Send me those questions using the Ask My Teacher button. Come see me during student hours if you need to. Otherwise, have a great afternoon, and I will see you all tomorrow.